Hi everyone, today we will be discussing the problem bike paths from POI 2018. This problem appeared in round 2, day 1. The problem goes like this. We are given a directed graph, that is a network that consists of only one-way segments linking certain intersections. A path from intersection U to another intersection V is a sequence of distinct intersections. Now the network has some properties. The most important property is if it is not possible to reach intersection U from intersection V, that is if there is no path from V to U, then there can be at most one path from U to V. Now given this directed acyclic graph, we have to determine the reachability degree. That is, for every intersection V, we should calculate the number of intersections reachable from V. So for example, in the sample graph that is given, from 1, the node 4 is reachable, the node 2 is reachable, and node 6 is reachable. Hence, the result is 3. From node 2, 1 is reachable, 4 is reachable, 6 is reachable. So again 3. From node, for the node 3, only 7 is reachable, so just 1. For node 5, 3 and 7 both are reachable, so 2. For node 7, nothing is reachable, so 0. So, how do we approach this problem? Let's draw this graph here. So, this was the graph that was given. So, let's try to make some observations. Say this node is V and this node is U. And we assume that from U to V, there is no path. But from V to U, there is a path. In this case, we are given that there can be at most one path from V to U. This was case 1. For case 2, from let us assume that there is a path from U to V and there is a path from V to U. Then there are no restrictions. There can be multiple paths from V to U, and in particular it might happen that there are paths like this. Now when in a directed graph we are given that there is a path from V to U as well as a path from U to V, we say that V and U are strongly connected. If there are multiple nodes A1, A2, A3, A4 up to let's say AM, such that for all AI, AJ, AI is reachable from AJ. So when I am writing it like this, I mean that AI is reachable from AJ as well as AJ is reachable from AI. Then this set of nodes is called a strongly connected component. In short, SCC. So how does that relate to our problem? Our graph might contain some SCCs, and since here we know that for every I and J, AI is reachable from AJ, then there can be multiple such edges. Here, our restriction that if U is not reachable from V, then there can be only one path from V to U, that does not apply because everything is reachable from everything. Now suppose that U and V are not part of an SCC and they are connected somehow. So let's say that V is reachable from U. Let's draw some other nodes that are also reachable from U. Now, for such a graph, there are a few options. Either it can be an SCC, which in this case is clearly not, or it can be a DAG, which in this case is also not the case because of the restriction that we were given that there can be only one path from U to V. This implies that the given structure here must be a tree, because we know that when we have a directed tree, there is always one path from an ancestor to a descendant, or there are no paths when we are talking about two siblings. But wait, it's not just a collection of SCCs and these tree structures. We can also have an SCC here. This might actually correspond to something like this. And then we can have a tree structure starting from here, which might correspond to something like this. Not only that, we can also have further SCCs down here. Now notice how I have represented the SCCs. I have represented this entire cluster of nodes as a singular node, which is kind of like a supernode. So a standard way to approach these problems is that we first compress SCCs. By compressing SCCs, I mean that I find all these strongly connected components and represent them using one node, which is this supernode. After this, we get a DAG. In our current problem, this is a special case where we get a tree and not a DAG. So essentially our graph is a special case of a normal directed graph, where if we had compressed the SCCs, we would have gotten a DAG, but since we have an additional constraint that if U to V is not reachable, then V to U only has at most one path. Therefore, we get a tree, a directed tree, and not a DAG. Now let's look at what we actually had to find. We had to find the total number of nodes that are reachable from a particular node V. First thing, if a particular node belongs to an SCC, that means for all nodes U that belong to the SCC, and let's name this node as X, X to U is reachable, right? Because you can reach every other node in your own SCC. Now what about the other nodes that we can visit? Well, it should be clear that in such a tree structure like this, let's say if our given node was this, then we can only reach everything that is inside its subtree. Now this just becomes a simple subtree size problem. Essentially what we have to do is calculate size of subtree for each node. One thing you should note is, after we had compressed our SCCs, there could have been some nodes which are actually compressed SCC nodes. These will have a size greater than 1. For example, in this scenario, for this compressed SCC node, the size here was 4. Therefore, when you are trying to compute the entire subtree size, you cannot just take +1, +1 and a +1 here. You will have to take up +4 here, not a +1. After that, we just report what is the subtree size for every node. Also note, after SCC compression, we get a forest instead of a tree, since the graph is not guaranteed to be connected. Let's look at the code quickly for this problem. First, I take in the graph. These are the normal edges, that is as they were given, and the reverse edges are required for the SCC construction. After taking the input, we compress all SCCs. In this function, we basically implement a Kosaraju's algorithm. First, we do a DFS, and then in a stack, we push all the nodes according to their DFS exit times. Then we keep popping the stack, and the way to find the SCC is by doing the DFS from the particular node using the edges of the reversed graph. So here we use the edges of the reversed graph. Everything that is reachable from that particular node is part of the SCC. We also denote the component of the node, that is after we are done compressing all the SCCs. This C is effectively the ID of the super node that we formed after the compression. After we are done with the Kosaraju's algorithm, we finally form a new graph, a new directed graph, which essentially represents our tree, or rather our forest. Next, we again set the visited array to 0, and then we perform a DFS on the tree. Note that we do not know what are the exact roots of each tree, but we do not need to know. We can just iterate over our children, and we just check that if the children is already visited, then we don't go any further down. Notice here that the size of node is the size of the SCC, and we are doing -1 because we do not want to include our own node as a reachable node. Also note that new node dot size does not really lead to overcounting because of this -1. Essentially, we do not want to count our own selves into the TP value of the node, hence we are doing this -1. But this also means that my children wouldn't have counted themselves in their own DP values, which is PE. Hence, I also have to add how many children I have in our calculation for the current node. That is why we have to add the degree of our current node as well. Finally, we just print out the DP of component of I, because every node inside an SCC is equivalent. Hence, we are referring to them using their component IDs. For normal nodes, the component ID of I will just refer to I. So this was a pretty short code. We are just doing a Kosaraju algorithm, and then we are doing a DFS on the newly formed tree, and then we are outputting the values. Hope you liked the video. That's it for today. Thank you.